Okay. All right. You ready? Everyone's gonna start. Okay. I will warn you. I'm slightly sleep deprived. That's the first thing. Second thing. This is intended to be a highly interactive talk. So ask questions, say things, whatever. Okay.
Call you clocks or sugars?
For now, we'll go with either. And then after we're done recording, I will go by my first name. So, okay, if anyone has any desire to follow along with notes, I have 2 different links you can see here on my website. At one point, I was writing a sort of textbook, I guess, and I will probably go back to doing that. So the first one is from that, and that is, I'd say, closer to the path we're going to go through this talk. And then the other one was a different talk I gave, more targeted to how do I explain this stuff in the context of trying to explain homotopy type theory. So that might be a little bit more off topic, but you'll still get a lot of useful stuff out of it if you're looking for notes. Okay. All right, the plan for this talk. First, disclaimer. I am not a computer scientist. I'm not even a type theorist. I'm just a mathematician. I'm a mathematical physicist if I had to be anything. I learned what I'm going to tell you for the purposes of doing homotopy type theory, and this talk is going to reflect this. There are going to be things about this that if you were in deep computer science, you'll be like, hey, that's not quite right, and like, just tell me. That's fine. Okay, next thing. This is going to be a very forgiving talk, right? The point of this is that almost everyone comes away from this like, they understand it. It makes sense to them. That might mean that there's like a third of you who are going to be very bored for a little while. So sorry about that. Okay, so first thing we're going to do, what is an inductive type and why do we care about them? Why is this a thing that we want as opposed to other systems of formalization? Second thing, all right, how do inductive types link to mathematical concepts, right? Now the reason we need to think about that is because when we're trying to use type theory in place of mathematical constructions, we give up a certain number of things. This was mentioned last week. We do constructive things. We require constructivity. That means that being able to prove something without giving an example of it is no longer possible. That creates a lot of problems, and we'll get to that later. But in particular for that one, I'm going to mention a teensy bit of category theory, and you'll just have to bear with me, but it won't be too serious. Third thing, okay, how types reflect propositional logic. So I don't know who's seen this before or how deep you've gone into this, but all of the things that you want out of propositional logic, minus expecting things that are true or false, you can do with types, especially inductive types, and we'll go through this. Proofs as functions, and we're going to do this very obviously. I'm going to show you a proof written in Rust. Okay, dependent types and their role in propositional logic, because I think that's probably the interesting thing here. This is a lean meetup. I know a lot of you at least have some familiarity with types, but seeing it as like okay, this is what the concept is, this is what it does, this is why it does it. We're going to do that there. And then we're going to do a little bit of live coding in Agda. And the interesting thing about that I hope you take away from this is that Agda has a whole-based programming paradigm. And that's going to be very different from the tactics-based paradigm that you may be used to if you've done a lot of lean. I must admit, have basically done no lean. I'm mostly a COQ programmer, if by contrast. So a lot of syntactic similarities. But the point being that like both tactics languages, Agda is completely different from that. And you'll see how. But okay, what is a type? Okay, this open-ended question. What are some things that you want a type to do? If you were like, we're calling this a type, we want to say like this is a type of things or something like that. Like, what are some things that are like types that we know about? Any answers? Yes, okay, obvious answer.
Definable collections.
Elaborate?
So I can get a collection of all these people here, but I would actually prefer to define them as the people who are interested in lean, are within 40 miles of this location, and so on. So I can have some definable first-order sentence, or if you'd like, some other sentence that will describe either exactly them or a superset.
Okay, here's a question. When you say that, do you mean I start with all of the people and then I restrict down under these conditions to the people who are interested in this thing?
I'd actually like to go both ways, but for a start, we'll do that.
Yeah.
The other way would be to go ahead and have something that I could build upon or elaborate and then add other things into my collection if I needed to.
Okay, I don't know who caught that, but that's going to be interesting. That's going to be important. We're going to...
Is he talking about the distinction of generating new lean fans, like by birth?
Or
Well,
perhaps going ahead and pulling the ones in from Marin or a few other places.
well, with proof erasure, they're all the same guy. So, all right. So something else, if anyone is in that direction, is you might think of a category as something that is like roughly like a type, and we'll talk about that a little bit later. Other things, I suppose, collections, as you mentioned, but there are a number of things you might associate as like, this is what a type is trying to do. What is a type? What is it for? What is it like, right? Okay, I'm going to say that as hard as it is to say that a type should be a type of things, that you should say like, this is the type of a thing, and all of the things that are like that thing go in there. That is actually not a way to think about them, not for what we're going to do, right? What we're going to do, actually, before we do that, let's do something that is not a type and talk about why that difference matters and what we're trying to get out of this, right? So who knows what defines a group? Who knows, who's done any group theory or knows what a group is? Raise hands. Oh, that's actually, okay, that's most people, all right. Okay, so we know it's a set of objects G with a binary relation. It's closed, so you can't escape the set using the multiplication operation. You have identities, et cetera, et cetera, et cetera. Okay, everyone's comfortable with this?
The operation should be total.
Meaning?
Meaning it should be defined everywhere. So it's not.
Oh, sure, yeah, of course.
It's closed, but it's also total. For every G and H, you should.
Yeah, we assume it has a domain, and the domain is fixed, yeah.
Well, also that's not a partial operation.
Yeah.
Thank you.
Okay. If I tell you I have a group G.
Are the cross, the dot, and symbol juxtaposition the same thing?
Sorry?
You have an X there.
Yeah, they're meant to be like, you know, dot, because it's a group. We want to do it by concatenation, but you always need like an operator, right? So it's a mess. But anyway, okay, here's a question. If I told you I have a group G, what do you know about this group?
Are you telling me anything else?
Nah. It's a group and I have it.
All the theorems you can prove from there.
That's true. You can prove things as a consequence of these like theorems. Here's a different question. If I tell you I have a element of the group G, what do I know about little g?
It belongs to a very special subgroup that's generated by G.
True, I suppose. Yeah. Anything else? What now? Yeah. Well, I mean that's the subgroup. You can generate a subgroup with it as a subgroup generator. Do we know what it is?
You only know how it interacts with the other.
Yeah. We don't know what it is. We know what it does, right? And we know what it does by restriction, right? When I said I have a set of objects G, I didn't tell you where those objects came from. I just said I have these, and I happen to have these things that do all of these things. Right?
I don't mean to get too metaphysical, but maybe you don't want to use the word know there. You want to say I'm given or I'm told about
sure.
G. Otherwise, if I'm presented as a vector of 6 numbers, and I might assume it's a permutation on those 6 numbers or something like that. Or if I assume that it's actually, oh, I'm supposed to flip this triangle point or something like that, I might think it's a group of isometries. So if I'm presented somehow with a G and G, what data do I know about G? It depends on the presentation.
Well, I mean, we're assuming we know it's in the group, right? Because you can be given an arbitrary bit of data, right? A string of numbers or something like that. You can be told.
Probably most pertinent to the discussion would be if I'm presented a whole bunch of code and I'm told G is in G, but I haven't access to the rest of the code yet. What do I know about G? Darn little.
That's the point.
Okay.
That's the thing. That is the problem, right? When we do mathematics, we have these things. We have to say like, I have things. What do I know about them? Nothing. Well, they behave this way, but I don't know what they are, right? And that's kind of the thing that we're going to go against today. So here's an example of a C-style enum, and we're going to do enums a lot because Rust inductive types are a very good model for this. Now, if I give you a value x and I tell you it is in the type alphabetic, what do you know about x? What data does it contain? What do you know about it? Yeah. I know what it is up to 26 different possibilities. I know exactly what data is contained in it. I know what it is, right? Here are different, okay, yes. For the purposes of this talk, the value of a type is that when you know what the type of a thing is, you know what it is, up to some like countable many things that you need to check out. right? When I tell you that I have a thing in this type, or that I have a type, and I tell you specifically it's an inductive type, I mean I can enumerate all of the things in it up to countable infinity, right? Okay, so a type is not the thing that it's supposed to represent, right? Previously we had alphabetic, it's an alphabet, right? And you can look at that and you could say, well, you know, there are all the letters in there, that's great. But really that just represents anything with 26 things in it, right? It could be numbers up to 26, it could be anything. But really, a type is not what it's supposed to represent, it is the way you make its members. And its names, unless you believe in the univalence axiom. Because if you have two different types and they're generated exactly the same way, there's no way to like unify them, or like you can make an isomorphism, but you can make plenty of isomorphisms, right? So unless you have a way to unify them, which is a thing that homotopy type theory does, and it says like, you know, any type with so-and-so generators is uniquely defined. But a type is not supposed to be anything. It's how you make the things in it. Okay.
By this suggestion, if I do take the univalence axiom, does it mean I can't make the names?
Well, you can choose names, but the names are sort of irrelevant at that point.
Oh, so if I have the univalence axiom, then I don't care about names.
Basically, yeah.
All right.
Yeah, I mean, I don't want to get into the univalence axiom now. I just want to say that a type is principally defined by the things that you can, like the ways that you can make something in the type, right? And then a lot of languages will also say that it's also defined by names and constructors, right? I can make two different types with the same constructor, same patterns, but if I give them different names, the type system is going to say those are different, right? That's just a thing with languages, but in a sense that doesn't matter. And some fields of constructive mathematics will say, I think that doesn't matter, and I'm going to make it not matter in the type system, right? But it's a bit of a moot point right now.
Other, or like is that even a judgment that's ever made?
Well, if you look at the univalence axiom as stated in homotopy type theory, it will actually say, yes, these two types are equal to each other, which, as you point out, feels kind of meaningless unless you're willing to say what that actually implies. Off the top of my head, I could not elaborate on that further, but that is a valid thing to be concerned about. Okay, what are some non-inductive types, right? What are some types that we can think of maybe that we're not really going to get away from making the inductive? Like we can't really enumerate all the things in them. Yeah.
Bottom?
Well, I can enumerate. I can enumerate 0 things. Now I want something that has things that I could never tell you all of the things in it. Yes, functions. So if we had a type of types, then maybe we could go about enumerating functions. We could say like, okay, well, the way that I make a function type is I take two types and I say that one of them is going to be the input and one of them is going to be the output. And so that arrow looks a lot like a function, right? And it takes two types and it makes a function type between them, except that I can't enumerate them. Maybe I could enumerate them if I had all of the types, but I don't, right? And some programmer is going to be like, oh, I'm going to make a new type, and then, you know, my system is cooked.
What about irrational numbers?
What about them? That depends how you're going about it, right? So well, that is a whole story. That's like that's not what I'm talking about. You could do okay. Do we want to spend like 2 minutes on real numbers? Okay. Okay. About which in particular?
About everything. What is why countable matters? Like this is the point about real numbers.
The countability doesn't matter too much. The point where I'm trying to make with that is that if you give me an inductive type, I can give you some operation to say like, okay, well, anything in this inductive type, I'm going to know what it is and I'm going to know what data is inside it. And if it's like some horrible stacked mess, I can deconstruct it down to like elementary bits of data at some point.
I mean, that's kind of trying to capture the idea of inductive.
Yeah, that's what I'm trying to say by typing inductive rather than just being a type, right? Because we have function types, but we can't enumerate all of the functions unless we know all the types, but that's a different story.
Yeah, but that's also, so you're saying it's not the existing type, but like potential types or something. Because like in any given implementation.
Yep. Exactly, and then yeah, that's the problem.
Maybe a little better, but I don't know how others do, but like I would be very curious about the real numbers.
Do we want to go into it?
I'm mildly curious which might build upon this. Would concretely enumerate the members correspond to something I think of as primitive recursive functions in recursion theory, and then the non-inductive types might refer to either general recursion or non-recursive collections. So I was going to suggest oracles for a Turing machine as a type of object.
I have to raise my I'm not a computer scientist flag. I followed you for half of that.
Okay, fair enough.
Okay.
I can also ask you later.
Yeah. Well, we should spend some time at some point talking about real numbers constructions because they are a whole thing, and there's all kinds of things to try to get around. How do I make this real number type that is supposed to have an uncountable number of things when my system makes countable things, right? That is a real problem, and it has a lot of consequences. Yeah.
Okay. So I'm willing to buy.
It's also a complex problem.
Yes, thank you. I'm willing to buy that type of types and function types are non-inductive just on your say-so, but I'm not sure that I can actually say that they're types because I don't know enough about types yet.
Yes. Okay. So that is the subject of a different talk. Unfortunately, that's where you have to get into universe levels.
So I have to buy that type of types is not just a type, but it's also a non-inductive type.
Well, that's where we kind of like pull the wool over it and say that like, okay, if you want to inspect that very closely, there are a bunch of things you can do to make that sane. However, if you do that, you add a bunch of complications, and those complications can be valuable, but you can do a lot without them.
Okay.
Right. So we're gonna explore some things that you do without them today, and run with me here.
So really, my takeaway is your last sentence. If you knew all the types, then I could make the inductive types, the function types inductive using this as a constructor, but I can't.
Sure. Yeah.
All right.
That we have some types that are not inductive, and there's not really a great way to get around that.
Okay.
Okay. Right. One more thing I want to point out on this slide is we have this notation, a constructor that has like 2 blank spots, and then it takes type, and then it takes a type, and then it gives you back a type, right? So then what is the property as a binary operator of this arrow, right? Because I have to give it 2 different arguments, and then it's going to give me an output, but it's not going to give me an output of type like print, like it's not going to take one input and then give me a new function, right? Well, it kind of does, but the point I'm trying to make here is that this is a right associative binary operator. I don't know who can, if that's too far down, but right associativity is a thing you have to worry about with this arrow. The arrow is not associative, right? You can't draw arbitrary brackets around it. The rightmost arrow is always the one that goes first, which is why you have this notion of like sequentially providing new arguments. Okay. All right, quick example. Here is the option type from Rust. It is a generic type, which is to say that it takes a type and then it makes you a whole family of types, and you could just imagine you have one of these types for each T you might pick. So this is an example of an inductive type. It has 2 constructors. The first constructor is none. It takes no data. It just is a thing, the same way that we had like the letter A in the alphabetic type. And then it takes it has a constructor called sum, which takes 1 bit of data of the type T, and now you have a stored bit of T, right? So the interesting thing about option and why it's used in like error handling is that you can say, all right, well, I might have the data you're asking for, but I might not, and you should be prepared for that. So if I take option T as an argument for some function, that function needs to know that it might not actually have the data or might not get the data it's asking for. So that's a thing you might do to build an error handling.
So some T might fail, but I still have none if I use option T.
Well, no. So if you take an option T,
right.
You might get some T, which maybe you're hoping for, and then you could process the T that's in your some T. And if you get a none, then you can't process it, and you have to say like, okay, well, whatever it was I was planning to do, I just have to not do that thing.
All right.
Okay, and here is the same thing in Haskell. So Haskell has a lot of the same things as Rust, but they call them different things. In Rust, they call them options. In Haskell, they call them maybes. There's similar things for, you could have a sum T and then like a different sum T, and in Rust, you would call that the result type. You say okay for like a successful version, and then you can have an error version that's like, I store your error handling result, and now you know which error happened. And in Haskell, that's called an either type.
Are we at the stage where I know or even care what some t gives me or what just t gives me?
Well, they're
still too early in the lecture.
Well, they're just different languages. That's just the names that those two different languages give you.
Right, but if I wanted to do a deep dive, and now may be the wrong time for that,
Yeah.
Would I care about what some t gives me, and would I care about if I were doing the other language what just t gives me?
What do you?
Because I don't know that, for example, some t could return the type.
So here's an example.
Yeah.
You have a
hold on.
a dictionary.
I think I see the problem.
Okay.
Some t is not a function.
Okay.
It is a constructor, right?
Right.
When you give it a t, it makes something in the option type.
Right.
Right.
It constructs something.
Yes, it constructs. So you shouldn't think of it as a function that evaluates, is the key thing. You should think of it as a function that explicitly does not evaluate. And so when you are sort of like parsing your code and saying like, I'm going to step through this, you get to some t and it doesn't do anything. It gets packaged. That is just an option now, and it gets sent off to something that takes an option. Right? So that's something maybe I should have pointed out, is that constructors are not, they're kind of functions, but they're not functions in the sense that they evaluate.
Well, it's kind of like a cast, right?
Like
You
a,
start with a type t and you end up with an option t.
sorry?
It's kind of like a cast. You start with a t and you end up with option t.
You can, well, you
Didn't
could,
really do anything.
you could cast if you have some t, but the point is that if you get an option, you might have gotten a cast.
Not the other way.
Yes,
Okay.
exactly. Okay.
And lean, by the way, is the same as Haskell. If you want to play with this, you definitely can. I think
Yeah.
the data keyword is different.
Is the type of the SumT constructor SumT, or is it of option t?
Sorry, how do you mean? What do you
If
mean?
I construct SumT, let's
Yeah.
say sum1.
Okay, no, some t is a constructor for option t, right? So what that means is if I use some t, it makes me an option.
Why does it find that like least upper bound of the type that it's in, rather than being a specific instance of sum of t, given that I just constructed it?
Well, that's the point of an algebraic data type. If I say I'm going to give you an option, you don't know which of these it is until you actually get it and then you look at it.
That's taking it as a parameter.
Yes.
But in the constructor.
Sorry, how do you mean?
Like, let's say I
Oh, do you mean like an option that takes an option?
let x equals sum t of 1.
You can do
Right.
that.
Is the type of x sum of int, or is it option?
It's option of int. Yeah.
Oh, okay. There's no subtyping.
Yeah. So good. That's a good thing to point out. Yes, it would be option of int. It's not sum of int, right? If you looked at the data, you would say like that's sum of like a particular number, right? But the same way that you would never look at a number and say like that number is int, right? It's not int. It is an int, right? Sum is an option, right?
So this is assuming a language without dependent types.
Yes. Well, Rust is not a dependently typed language, right?
But it does have some subtyping, but it doesn't come up in this context.
Yeah. Okay. Where was I going? All right. We basically argued through that. Okay. Some things about inductive types. Okay. Okay. So some takeaways we need to get from this. This is where the sleep deprivation is coming in. A thing always belongs to one type, right? That's how this works. They're not like sets where you have like a thing could belong to multiple different sets. A type is not a set, is a thing that tells you how its contents are made, right? So just like the option type previously, if I have an option type, I know it was made only two ways, right? One of two ways, right? That's why, okay. So in particular, the idea that you would say like X is in big X, that is a proposition, right? That is a falsifiable statement. When you see something like this, where you say X is of type X, right? What you should think is that little x gets its existence from big X, right? Like to say X is of type X, that tells you what little x is, right? Or what it could be, right? You wouldn't falsify that, because if you were to falsify that, you'd be like, okay, well now I don't know how X is made, right? So that's not a falsifiable statement the way that like set membership is. And we've got to no subtypes because the thing only belongs to one type.
So if we're trying to avoid set membership, then we say, all right, let's enumerate big X if it's an inductive type, and otherwise let's construct things out of X if it's a non-inductive type. And if we keep going, our little x will appear at some point, and then we can go ahead and deal with it if it's type X or the X colon.
Sure. I mean, well, you can build sets out of types, right? But that's a whole thing, right?
I understand, but the idea is I'm trying to reframe it so that I can turn X and X into a proposition, and I can turn X colon X into something. And right now, coming from a recursion theoretic background, I can say, oh, eventually I'll generate X if I use all the different rules and try to generate
Yeah,
the
sure.
type X.
Yeah.
I can generate all the things there, and eventually I'll come across X.
Yes,
Okay.
exactly. Well, that's one way to think about it, but the way that I would prefer that you think about it is that you look at little x and you say, big X tells me how I can look inside little x, right?
Oh, okay.
Okay.
By the way, in Lean, you can write both of those, and it's a common confusion for newcomers.
Yeah, well, so a lot of the proof-assistant languages will add syntax tools that make a lot of those, like the sort of mathematic notation, identified with the type theory notation, and so there's problems that arise from that. Okay, we're going to talk about categories for a little bit, just because they point to something that I think is really interesting and very valuable for what we're going to discuss. Okay, so 3 things, which I don't remember. Categories are always defined not. Okay, so when you have a category is defined. It has a few properties, but before those properties, it is a set of objects, right? So if I have the category of groups, I have objects which are groups, and then also a pattern for what the arrows, what the functions between those objects look like, right? So groups have group homomorphisms, right? If you were to have something that's not a group homomorphism from one group to another group, you would have to think, well, that's not respecting the group structure. That's it's just like a function map. You've just like arbitrarily treated these as sets, right? And there's a similar thing for vector spaces, right? If I have a map from one vector space to another vector space that is preserving the structure, it's a linear map, right? And of course, sets don't have that much structure, so their morphisms are functions. Yes?
So I mildly disagree with this statement.
Sure.
But if you said some categories are always defined this way, then I'm on board with you because I did a fair amount of universal algebra in my time. Is there a reason you're choosing function as opposed to morphism here?
Mostly because of the stuff we're going to get into. Like, I have 2 key examples I want to point to.
All right. So if you say some categories, then I'm on board with number
Yeah.
1. Okay.
That's the like categories based on sets. I thought about adding disclaimers and then
No,
really.
There are relational objects and there are other things.
Yeah,
for
okay, I know
relations
those ones,
that you
yeah.
have to do that. So if you say some categories and the ones we're interested in are those with functions, great.
Yeah.
I'm with you.
Yeah, that's what I want.
Okay.
Okay. Okay. So neat thing about category theory is that we can take common mathematical concepts and define these patterns that we see like across many different systems of mathematics as a diagram of arrows between the objects, or arrows being the functions, or as you said, morphisms perhaps. Okay, something very interesting about category theory that we're going to use is that it often tells us that whenever we have one of those patterns, one of those like things we see across mathematics and we can describe it as a diagram, we get something meaningful if we flip the direction of all of the functions. And I'm not necessarily talking about inverses. I'm saying you just you take the diagram, you flip the arrows, you say, okay, well, what would these functions have to be in order for this diagram to still work? Yes?
So, just there are categories in which you cannot flip the arrows.
Sure,
right?
yeah. I believe so.
I'm just thinking of like the modulo operator.
Wait, it's not an endofunctor. It goes to an opposite category, right?
Okay, got it.
Yeah. Okay, so the Cartesian product, everyone's familiar with Cartesian product, tuples, etc. This is the diagram for it. And what we have is, the idea is, if you have, your type X and your, set X and set Y, or yes, but even better, object X, object Y, and you have some Z that can map into both X and into Y via Fx and Fy, and you know that you have this other thing that maps into X and Y via projections, then you can make this new F where you sort of fuse F and Y, and you say, okay, well, if I know that this can turn into that, and I know it can turn into that, I'm going to make a pair. I'm going to say, okay, well, the projection, what was I going to say?
There exists a map.
Yeah.
Such that.
I could just say okay, well, let's make a, open parentheses, fx of your element of z, That should be an, that should be an f of x, f of y. My mistake. But the point is that you can sort of take this pattern where you're like, okay, I'm going to send this z to. There are a few things wrong with this diagram. Huh?
Did you want little x and little y?
Yeah, well, that should have been f lower x of z. There are a few. Hang on. Do I have a whiteboard? I could just fix it right now.
Here.
Sorry.
It doesn't have to be projected on a whiteboard, does it?
No, it's on a wall.
That's the wall, and we are not allowed to draw on it with indelible marks.
Yeah.
Just spoils it for the next speaker.
Well, there's nothing wrong with that, is there? Okay.
Well, I mean, it's ironic that we're talking about the projector operator.
Okay, all right. What that should be is z to f lower x of z.
Little z.
It's just a large little z. Okay, well, we'll give that the line so you know it's a mapping, right? And that should be f of fy of z. And then I have this object I can make in the middle, defined by this map where I just do yes, and then the projection operators. Oh, I've run out of space for that one.
No problem.
Okay, but you get the idea, right? I have this pattern, and I can say, all right, well, the fact that I can draw this diagram tells me something about like what ought to be in here, because I know that like it has to respect these rules. I'm sure that there's like some weird category where you wouldn't end up thinking of x times x Cartesian product with y. Well, also it wouldn't be Cartesian in that case, where it doesn't end up being a tuple. But for a lot of different categories, you can say like, well, if I'm going to respect this diagram, I end up just like storing 2 bits of data next to each other, right? Okay. All right, here is how you would represent that, or in Rust. Now, obviously, that was a mathematical thing I just showed you. And because it's a mathematical thing, it is trying to say as little as possible. It is prescribing you have to follow these relations, and from there, properties are supposed to come out. And then when we do the inductive type version of that, we do it the other way around. We say, okay, I'm going to make a thing, and that thing is going to obey these properties. But first, I'm going to tell you how it's made. And from how it's made, I'm hoping that it's then going to obey the properties I want from it, right? So we make an inductive type. We call it pair. And we're making it generic, so it could be a pair of anything, right? Or a pair of any 2 types. And it has one constructor that requires that you give it 2 bits of data, 1 from the first type and 1 from the second type. Is everyone okay with that?
No, because I'm seeing just the types being specified there, not arguments from the types or things belonging to the types.
Oh, like you mean you want to see an example of it?
No, it's you say pair big X comma big Y.
Yeah.
And since I'm stuck in the set theory world, I think it's operating on the type X
sorry.
as opposed to operating on something
Right.
constructed from the type X.
Sorry, this is Rust syntax for a generic type. What that means is that for any 2 types X and Y, I will construct a pair type between them, right?
Okay.
And so this pair, when I have a specific X and a specific Y, the pairs of X and Y is,
String, for example, which you have on line 4, by the way.
yes, right? This is an example of a specific pair, right?
So pair,
Bit-
the lowercase pair.
A lowercase
on
pair
line where
is a
one
yeah.
is not yet specified. And
Oh,
you're
no,
about to do it
specified
in the
there.
other line.
Well, it's just Rust syntax.
Oh, that's Rust syntax. So
Yeah,
I
you do
assume
specify, there's nothing more to specify about.
Yeah.
Yeah. So this is the constructor. This is how you make a pair, right? This is the pair type, uppercase, lowercase, right? There are a bunch of ways to do this, and you're right to be confused. But I was just sort of assuming, I was hoping that as many people as possible would know Rust, and that's one of the nice things about Rust. It's very popular right now.
that does not include me.
I'm
Okay,
sorry.
No problem. I'll keep going.
Okay.
It reads better in lean.
Yeah.
You could use C++. Yeah, that's right. Could have been worse.
Could I? Does it have algebraic data types? Nah.
Templates. Remember, right, so you can define pair, but you can't define pair.
Huh?
You can define capital pair, you can't define lowercase pair.
Yeah, you can.
Okay, maybe I shouldn't have named this then because maybe it's confusing. This is not the constructor, this is a pair, right? It's taken as an argument to this function.
Okay.
Okay, never mind. Okay, so what do I have? We have the two projection operators that you saw before. This takes a pair and it says, I'm gonna look inside this, and looking inside this is simple because it only has the one constructor, right? So match says, I'm gonna look inside this, 1 second, and then looking inside this says, okay, well there's only one constructor it could have, which is the lowercase pair, which takes 2 bits of data, and I'm gonna give you back the first bit of data and throw away the second one.
So I just want to point out, the first lowercase pair in that line is not the same thing as the second lowercase pair on that line, or the uppercase pair on that line, but it is the same. The first lowercase pair on that line is the same as the lowercase pair on the previous line.
That's
Do you want to go and
my bad.
point at it, or yeah?
Okay.
Just use line numbers.
Sorry.
I'd rather he
This is the
Yeah.
same as this, but this is
Okay.
not the same as this or this.
Okay.
You should have chosen a different name for this.
I should have, yeah,
Like
yeah.
Maybe.
I've made it a bit
Thank you.
complicated.
Does the existence of a constructor imply the existence of a deconstructor?
Yes. That's what it's doing here.
Yes. But I'm just saying, like, in all cases.
In a like broad sense of like the theory, yes. In Rust, you often wouldn't think of it like a deconstructor because there's no deconstructor object. You just deconstruct it,
Yeah.
right? And that's what match does, right? Match says like, okay, I'm gonna look at all the different constructors it could have been, and I will do a case breakdown for what you should do if it was each case, right?
Give you extra stuff inside.
Yeah.
Is there a
Can
strong
we suggest we
relationship?
move away from the Rust? Give us the Rust meetup.
Well, yeah.
Okay.
I'm done.
Well,
We'll
it's like-
move to the lean translation in a moment, but I would like to understand this. Is the uppercase pair in line 4 related in any way to the uppercase pair in line 1?
Yes, so that's you see uppercase pair colon. This is specifying that this constructor is a constructor of this type,
Okay.
right? So the type constructor.
But you could have called it Q, for example.
What now?
You could have called it Q, for example.
Yeah, I could have called all sorts of things, and I'll do that later. But
Anyway, we have these two things,
Yeah.
which we almost understand.
well, so they're the same things from the previous slide, right?
Yeah.
So we have the pair, and we have the projection operators, which you saw before, right? So that's the pair thing,
Yeah.
projection operators,
Right.
right? And we just turn them into code. That's all.
Okay.
And then we have the same way on the last slide that this implied a way to take your fx and your fy and merge them into just one f.
Okay.
And then we have your merge operation the same way, right? You take a function fx and a function fy that goes from z to x and from z to y. And I say, I'm just going to make a pair out of fxz and fyz,
Okay.
right? So the same thing we did in the diagram, we just do in code. Is everyone okay with that? Cool.
I can start getting my head around it as long as I understand that fn of f this is how we're going to construct this particular object of this type, in which case, what is the type of little f on line 15, first instance?
Okay, so what we've done, so this is a type of a function pointer, right? So we're saying that this function takes functions as arguments,
Right.
right?
That's
What
line 12.
what this is doing on line 15 is
Yeah.
defining a new function,
Okay.
right? And then I personally wouldn't trust Rust to treat the function definition as a result, so we're just giving it back on the next line. We're saying
Okay.
this function f I've made, I'm just going to give it back.
What does the f on line 16 do?
Oh, that should have
That you need to assign it.
I should have put a pair in there. Whoops. Sorry, f on which line?
On line 16, there's a solitary f.
Yes. That f is this f,
Okay.
right? I'm giving it back. I'm saying like that's the thing we're going to output.
In Rust, if you have an expression at the end of a function without a semicolon after it, that's the return value of the function.
Lovely. Okay.
My apologies.
No
We're not
problem.
going to be able to learn all of Rust.
Yeah.
It's something we need to.
No, but just
I know
Okay.
it's fun to learn Rust.
duality time. Hey,
Duality
let's go
time.
back.
Yeah, we're going to take the same diagram. We're going to flip it, right? So now all of our arrows point in the opposite directions. If I have an x and I have a y and I have a z, and I have fx that points into z and fy that points into z, I can construct this x plus y type, or thing, object, and it has, instead of projection operators, I'm going to call them inclusion operators, ix, iy. Anyone want to take a guess what kind of data is contained in there? Not you, I know you know. Yes.
Or
What now?
it's like the opposite. If the tuple is and, then you want or.
Yeah, roughly, right? So something in this could be from that or could be from that, right? So previously, we would have.
In the same way that like option is none or some.
Yeah, right? So then the pair, like the pair said, I need data from both of you, right? And this is going to say, I need data from either of you. It could be one or the other, I don't care, right? So that's that here, right? We have the sum type, and it has two constructors instead of one. So the same way that you were thinking about like constructors and destructors being kind of like matched in some sense, this is where that starts to matter, right? The previous thing had two destructors. That was the projection operators, right? This has two constructors and one destructor. Hang on, is that right?
Let's all confuse the C++
But it
people,
is-
huh?
Yeah.
It has two things which look like injections to the set
Yep.
theorist, and it's got this merge thing because, hey, we're trying to merge stuff so that we can do
Yep.
construct the F from our universal object, which is a disjoint union of things, so we can use it in code down the line.
Yeah, so, well, let's look at the way that we do that, because what is this F that we're giving back, what is it doing? It is saying, whatever thing I get from this sum type, I'm gonna look inside it, I'm gonna say, okay, did it come from X or did it come from Y? If it came from X, apply F of X. If it came from Y, apply F of Y. Right? Does that make sense to everyone? So what I've just said is I said, okay, well, I'm going to, I don't know which of these X of Y it could have actually been, but like, I'll deal with it on a case-by-case basis, right? I have this F of X, or this Fx that works for X values. I have this Fy that works for Y values. I'll use what works.
So basically, you've turned the match operator into a higher order function operator.
I guess, I don't know, I will, if you're interested in what we're doing right now, your mind will be blown in 5 slides. So, okay.
Turn the camera on him.
Live reaction. Okay, all right, the point of all of this. Mathematics, I'm going to say, defines things restrictively, and I'm not like, this is just sort of a polemical statement. If you want to disagree with me, you can do that afterwards. But what that means is that,
Go ahead.
what that means is that when I say I have a mathematical object, I have, in some sense, I've said, all right, well, imagine all of the mathematical objects there could be, and I'm only going to work with the ones that obey certain conditions that I like, right? We saw that with groups, right? All of the sets there could be, I have a set, and I have some relation on it, and the relation has all these properties. And I'm not saying it could be any relation, but it comes from any relation, right? I don't have a way to make relations in some like inductive way, but I can say like, okay, if there's a binary product, I'm going to expect this binary product has all these properties, right? And so you're restricting down from the set of all things that could be to the set of all things that could be that obey these nice properties, right? Inductive types do in the opposite direction. They are prescriptive. They say, this type that I have, I know how I make things in it, and I don't know what properties it's going to have after that, but I know how it's made, and then I can figure out which properties it has after I know what it is, right? Okay, I think we basically covered that.
I have a suggestion.
Yes?
Try non-prescriptively instead of restrictively, because while restrictively is sort of true, it's sort of not true.
Yep.
But there are times when you have a non-prescriptive definition of something that I think applies more to the philosophical art of where you're going.
Or constructively, maybe.
Not constructively. You want to say non-prescriptively for a particular reason, in that there are ways where you can go ahead and extract things, or maybe, if you have axiom of choice, a whole bunch of things at once.
Well,
you don't really particularly care.
That's why we're not doing axiom of choice yet. That's a whole other situation.
Exactly, but I recommend non-prescriptively.
That's fair, okay.
You can also borrow the linguistics terminology of descriptive versus prescriptive.
This has its own problems, but yeah. Knowing exactly how the elements of an inductive type are made means we get to write elimination rules for all the ways you would destruct a thing and make something else.
That's the
Subtractively and additively, or you could do many other things.
well, so the thing I'm trying to point to there is the matches we did earlier, right? That you can look inside a thing and you can say, it could have been any of these things and it couldn't have been anything else, right?
Do we have to use the word destruct? Can we say deconstruct?
You can. I use the word destruct because destruct is the keyword that is used in COQ to do exactly that.
I see.
Right,
Okay,
that's just- that kind of got
we're
imprinted on me.
foreshadowing.
Well, we're not doing COQ today. It's just that that word is it's
Well, for your next lecture.
elimination, I believe, is the word that's used in the literature. People say introduction rules and elimination rules.
Right.
I'm getting thumbs up from a real computer scientist. That's good. Okay.
We're making real computer scientists here in this group.
Yeah.
There's one of them.
Okay, all right, now we're gonna do proposition types. And as you foreshadowed, a lot of the things we've done already are going to be all the things we need for propositional logic. But, okay, what do we need for propositional logic? If I told you we're gonna do some propositions, what kinds of things do I need? If I'm gonna,
Capital letters.
that's a great start.
Yeah.
The Boolean crap.
What now?
The Boolean crap.
Yeah, well, okay, all right, and, which Boolean crap? Huh? We need what now?
Yeah.
Yeah. Okay. We need a Boolean crap, and we need more Boolean crap, and we might need some Boolean implication crap.
We need at least true or false.
Yeah.
And either and or nor or implication. Well, you can construct everything. You don't need all that stuff.
Are you sure we're not computer scientists?
Minimal amount of things for propositional.
Okay. Okay. Huh? Okay, that's why I put the ellipsis there. And we're going to do this later, right? Because we need dependent types to do this. Okay, well, we're not going to get to universal quantification and existentials because to do those we need dependent types. And right now we're going to do all the propositional stuff we can without dependent types. And we're going to.
This is the logic of propositions. It's not the logic of quantifiers like first order logic.
Sure, we're gonna. Well, I wasn't expecting quite a literate audience, and this works great when people don't know what comes next.
Yeah.
Okay, so all right, a proposition type is a type which is we say that the proposition type is true when it is inhabited, right? Now this seems trivial because all the types we've looked at so far are inhabited by default, right? We have a sum type. It's like, well, what's in it? You know, in left or in right, or we had like the product type, the pair type. What's in it? Pairs, right? We're going to say that a proposition type is false when there's nothing in it, and it's true when there's anything in it, right? Now, proposition types, the way that we're going to discuss them right now, are not actually meaningfully distinct from types, right? You could look at the sum type and say that's true, and you wouldn't be wrong.
That's or. The disjunction of.
You're getting too ahead. You're too smart. Okay, so here's our true type. Our true type is literally just an enum with one constructor, and it's true, right? You could do the same thing with the alphabetic we had earlier, right? Alphabetic is just true 26 times. Okay, and our false type is just the empty. Now, the true type has a lot of different names in a lot of different contexts. In Rust, you'll see this parentheses over and over again as a type, and we call that the unit type. It is generally called the unit type, or the top type, or the bottom type was also mentioned for false. I'm not familiar with void.
Void is more of a unit type.
Is it?
For C or
Oh,
Unit is distinct from any, no?
So C's void is kind of shitty.
I think so. Yeah. Well, because unit is specific, right? It's
It is
the.
specific unitary.
empty in TypeScript.
Yeah.
Huh. Oh, I didn't know that. I don't know anything about
False is
TypeScript.
bottom.
Yeah. So false is, we call that bottom, we call that empty, we call it, later we're going to call it a funny zero. But yeah, so, okay. Well, everything that I attempted to foreshadow was just kind of like pulled out from under me. Like, yeah, everyone knows this already, apparently. So, okay. Our logical conjunction, we call this, the P and Q, is our product type, right? The reason for this, it should be intuitive at this point. If a thing is true when it is inhabited, the only way that we can make a pair that has something in P and something in Q is if you have something in P and something in Q, right? So you have to be able to, oh, actually, hang on. Did I skip past? There, yeah, no, I should have mentioned this. We call those members of a proposition type a witness or an evidence or a proof, right? That's
All
the
members of a true proposition type, a witness or evidence or proof.
of any proposition type.
Okay, so then
You could say there are
there's no proof of false?
There's no proof of false. That's why it's empty, right? Like I say, okay, I have my inductive type. How do I make things in this type? I look inside. Oh, I don't. That's the point.
If we have a proof of false, how do you logic it for yourself?
I can prove lots of stuff, but
Well, I mean,
all right.
did you use the axiom of choice to do it?
It depends on the day. Tuesdays
Yeah.
I use it heavily. Rest of the week, not so much.
Okay, but this nomenclature will be handy because when you say like, okay, I have this type or I have this proposition, you want to be able to speak about the witness that you're trying to make, right? That's the point. You don't make a proposition because a proposition could be false, right? If you're trying to prove a theorem, what you're trying to do is you're making a witness of the thing that you're trying to prove, right? Like I was saying earlier, the witness of P and Q is the pair P comma Q, right? Makes perfect sense to everyone? Okay, and the P or Q, this everyone knows, everyone sees where this is going? Okay, yeah, too foreshadowed. P or Q is the coproduct type or the sum type, which is if I have something of P or I have something of Q, I do in left P or I do in right Q. Right? Everyone's okay with that? That makes an OR. P implies Q. That's just a function type, right? If I have something of P, I can turn it into something into Q using the function, right? Everyone's comfortable with this? Okay. What's not P?
P is a function from P to false.
Yes. I was hoping it would take a little longer than that. So okay, a function must associate an output to every input. What happens if the input is empty? If I say I have a function from empty to P, or like some type or something like that, what does that function look like?
Can't do shit.
Well,
In set theory, we've defined it already. It's the empty function, and you can't
What?
do much with it except instantiate it as a member of some other type.
well, so we're starting with the input is empty, right? So if the input is empty, can't do shit, right? But it exists, right?
Yeah.
That's a witness, right? So false implies anything, right? Because you have a function from empty to anything you want, right?
And in code, this is like appearing in my head as null as instance of some type T or something horrible like that.
It's a function that doesn't take any arguments and return to
But we will see this literally later in Rust. But yeah, okay. If the output is empty, then that function can only exist if the input type is empty, right? Because I have to find an output to assign to every input. If I have an input and that input has members, it has things that might need outputs, and I don't have outputs to give them, I can't make that function, right? So if I have a function like that, that tells me there are no inputs. That's good with everyone? Okay. So what that means is that the negation of P, not P, is the type of P to the empty type. Okay. Here is, as I said earlier, proofs as functions. Literally, we have a function, we have a theorem. If you have P or Q, and you have not P, then you have Q. Everyone agree with this? Yeah. Okay, and here's how we do it in code, right? So using all the same things we did earlier, I have a trivial function. And this is a generic trivial function, so the point is it'll work for any proposition. I can prove anything I want if I have input false. If I actually find an input false, I say, okay, well, how am I going to make my Q? Well, let's look at all the different kind of X's I could get. Oh, there aren't any. I'm done. Is that okay with everyone? Okay. Then how do I actually prove this? If I say, okay, well, I want to make a member of Q, and to do it, I have a sum type member of P or Q, and I have a function from P to the empty type. And that maps to this proposition. Everyone follows that? Okay, what am I going to do? I'm going to say, look inside S. Did it come from P or did it come from Q? Now, if it came from Q, that's easy, right? I just give back the Q I got, right? I have my proof of Q, I'm done. Now, if it came from P, what do I do? Right? Because that can't happen. That's not supposed to ever happen, right? This is supposed to tell me that I am never going to get a member of P, right? So what do? I say, well, it's funny that you claim you gave me a member of P because if you did, I can prove false is true. And if I can prove false is true, I can prove anything I want, right? So here's a funny thing. When you do this stuff literally using you look inside all the types and you say okay, this is what my negation is. I'm actually doing a map to the empty type. This does not absolve you from dealing with impossible cases. what it does is it says, if you are in an impossible case, you need to figure out what your proof does in this impossible case, you just say, well, it's impossible, and if it's impossible, then anything's possible, right? And then you say, from anything possible, I do the mediocre proving Q thing I wanted to do. And then you resolve your cases. And that's, yeah, I was as amused as you are the first time I realized this. It's like, yeah, you use your, I can prove anything to prove that one obligation you had, which is just a low little Q. But all right, is everyone comfortable with this?
I'd like to run through one example where Q is the empty type.
Where Q is the empty type.
No,
That would still work.
It would still work. I'd like to understand why.
Well, why, in which way?
So, how does it work? How do I get something that establishes that Q actually is false?
Well, this would not establish that Q is false, but
Right.
if it happened to be false, to be false, what would happen is you say, okay, well, I want a proof of Q, right? And this theorem says even if Q is false, right? You claim that you run the theorem only when you have an S, a member of this sum type,
Right.
and only when you have a proof that P is empty,
Okay.
right? So if this theorem were to run, then you had to give it this and you had to give it that, right?
Okay.
Right? Because you gave it this, you know that you never gave it this, right? You never gave it in left P,
All right.
right? If this function were to be running, and for some reason it was running with an empty Q, then you would have had to have given it that somehow. You would have had to have given it proof of false,
Okay.
right? Which you're not going to do.
you can't run it. You can never get into this function if Q is empty.
Garbage
The-
in, garbage out.
The theorem won't run, but it still exists,
Yeah.
right? So you can have a proof that like it's not going to execute meaningfully, but the type checker is going to say that's valid. That thing exists.
Okay.
Okay. Yeah. So we would call this whole function a witness of this type of P or Q to taking another argument of not P gives me back Q. With the caveat, as I said earlier, that needs parentheses.
Right. Associative.
Right associative.
Can you draw this as Boolean logic gates?
Probably. Well, okay. If the not is
Would a truth table help?
Yeah, implies is kind of
Imply-
game with the logic gates.
Yeah.
Yeah, implies would be my only question.
I mean, in imply, you can do the implies gate as an and or an or with one of the inputs negated. True.
But the whole point of this also is that like it's assumed that P is false, right? So the truth table or the logic gates isn't particularly meaningful because you just have to say like whatever it is that you might want P to be, we just set it to false, right? And then so there's not much enumeration to be done there about like all the different truths and falses there could be.
It's also, just to your point, like if P goes to false, then that's also saying that there are no other functions associated with P that go to like something else, right?
Well, I mean, you could have P go to other empty types, right?
Okay.
Any other false type, you can still have a map from P to that.
Got it.
But that's the thing. If false, then anything, including other false things, right? As you say. Okay, here's the same thing in Haskell, and I wanted to give you this as a point of comparison, just because we're going to get into Agda, and Agda looks a lot more like Haskell than it does like Rust. But if everything, you were okay with everything before, this trivial function, we're going to do it again, just like this. And so the generic typing is we just have a type here, x. So yeah, no, Q is the generic type. And we do case of, which is our Haskell version of match. And then, of course, there's nothing, because there's, yeah. And this is a type alias. We've literally just said, okay, well, I can say negate P, and that's just, it refers to a different type that already exists because, function types already exist. I have data false, it has no constructors. Some type, as you like before, and the same thing.
When you say data false in Haskell, there is no data.
Yeah.
False is not data.
Yeah, I mean, like,
Data is never false when you have it.
well, okay, so that's a useful thing though, because I remember I mentioned that option is used for error handling, right? And there's a version of that where the non-type is not none, it holds something else, which is your error type, right? I could put in that error type empty, And then what I'm saying is this thing that is returning a result should always evaluate properly and never throw an error, right? So that can be useful, right? You can use that to close off branches of code that you don't want to happen. But doesn't matter to us because we're doing proof assistance. Okay.
What was the, sorry.
Go on.
Back question. What's the of on line 7 doing?
Of on line 7. Oh, okay. So in Haskell, you need that to, it doesn't have like case X and then open parentheses. Of is like it says you enter this. And then it does something with white space. It's just match, it's the match syntax. Okay, as you were pointing out, we never finished our list of logical operations. We need conditions, we need universal quantifiers, we need existential quantifiers, right? Do these make sense to people as like reasonable things that you'd want, right? If I say I have a proposition, P, that proposition refers to one thing that could be true or false, right? If I have a condition, I might want to say like, okay, I have some type big X, right? And I have a proposition that could be true or false for each X, right? Like, maybe X is the natural numbers. And I say, okay, well, I'm going to give you a natural number. I want you to tell me if this is prime. Good luck, by the way. But, that's a question you could ask that is particular to each natural number, right? That's a proposition that relies on that natural number and is particular to that natural number and is true or false for each of those natural numbers, right? So we need some way to deal with that. We need universal quantifiers that say, okay, well, we have our conditions. Can we say that that condition is always true on that type, right? And we need existential quantifiers to say that, like, okay, I have this condition. Is that condition ever satisfied, right? These seem like reasonable things? Anyone have any guesses how we're going to do this? Have I foreshadowed at all?
I'm hoping P of X will become a propositional type.
Close.
Okay.
Well, hang on. P of X, specifically P of X, will become a propositional type. Oh, you're a co-host now.
I guess so.
Yeah.
We're talking in the audience.
Is the guess that you use Agda and then there are for all and there exist keywords?
Actually, okay, we're trying to do, for now we're trying to do something broader than just Agda. This is, the thing that I'm explaining is for broader dependent type theory, right? And you can do dependent type theory in all kinds of contexts. Specifically what we're aiming for is Martin Love dependent type theory. So sure, okay, those keywords exist in a form, or certainly you can make them in the way that you might want to, but that's not the point, right? This isn't just about Agda, this is about any sort of like language that mimics that type system you might want, right? But still, how would you go about this, right? Your hint is it's dependent types. What are we gonna do?
We inspect the type of the object that it's being constructed and try and like propagate that through because we actually have an instance of the value of type T.
I don't think, I'm not sure I understand what you're saying, but if I do, I think that might be the wrong direction. Let's jump into the first one though. Okay, dependent families, right? Look at this. Does everyone have an idea of what this means?
Oh, you have
just
the
looking
type.
Well, of course I have the type, but like I have a function that goes from the thing I want to do a condition on and makes a new proposition in that type, right? So mind you, these type families, I'm not assuming they're inductive either, right? You just like have this collection of things. They can be inductive, we'll look at those. But off the top of our head, we're gonna say like, okay, well, a type family isn't by default inductive. It might be, that might be something for someone to tell me later. But okay, if I have a type family, and I say I have a function that goes into that type family, but specifically the member of that type family corresponding to the input that function took, right? I say,
53.
what now?
Like 53.
Yeah, okay, I have a function. The function is this thing prime or something? Oh, no, actually, I shouldn't do that one.
Is it even or odd?
Sure.
But you
No.
like partially apply the function to its actual value.
Well, so here's the thing, right? If the function is going to go into a condition type, what I'm saying with that, think about that. If the output is a witness of a proposition, what I'm saying is every time you give me one of those inputs, I can prove that proposition is true. So you would not want to do is even because that would assume that all of the natural numbers are even, right? You want something that is actually true for all the natural numbers. You could do that for like an induction rule, which we'll do later. But the point is a dependent function, because it says, all right, well, whatever your type family is, every member of X, I'm going to give you a witness in the proposition Px, right? That means it's going to prove it for everything in the type family, right? This is our for all.
So in Prolog, this is a rule.
I don't know enough
I
Prolog.
don't think so.
Like, okay.
No, in Prolog you have something a little bit different, and we're actually trying to go ahead and deal with things that are more constructive, whereas Prolog, you're not constructing things this way. You're trying to determine the truth value of various statements.
Well, yeah, so something I should point to about this is that if I like make this function f, I actually have to have the function, right? So I have to be able to say like, okay, when I get this x, I know what to do with it. I actually know how I take that x and use it to make a witness, right? So that's the sort of difficult part of this. Is
Is the type actually the type of non-false types?
No, I'm going to say. It's the type of all types, right? And then if you were going to try to say, like, I can prove a false, right? Maybe you have, like, I don't know, if I have this type family, I could negate this, right? I could say, you know, negative P, and then what that would be is a type family that, actually, would it
No,
be?
I'm just a little confused. You said that, you know, like, my understanding was that if I have this family,
Yeah,
and I provide an input, right?
to the type family?
To the X, like, yeah, to the
Yeah.
then the output would be some type, which would be a witness of the proposition being true for
okay.
that input.
This makes the witness, this makes the proposition, right? So this makes the Px, which is the specific, is P true for X,
Okay.
right? And then F, if it is a dependent function from X to the type family P, then it is a function that says, I take an X and I give you a witness in the type Px.
Yeah.
If this is a little confusing for now, just run with it because it will become very obvious when we actually see Agda.
I'm just trying to understand what happens if, like, Px is the false type. Like, you know, like if on the right I have false.
Yeah, okay, so that could exist, say, for example, if P is this natural number even, right?
Yeah, okay.
So if P is this natural number even and X is the natural number type, right, that's going to be false for every second number.
Right. So
Right.
so my type family that formalizes that proposition kind of intuitively has to take even numbers to some non-empty types
Yes,
and odd numbers to empty types.
exactly.
Okay, thank you.
Yeah. Okay, so dependent functions will sort of generalize our notion of for all, and we'll
To be absolutely clear here, dependent types, you've given us two things here.
Yeah.
Are they ingredients to make dependent types, or are each of these dependent types in and of themselves?
That might be a more sort of semantic question that I am not super equipped to answer. I think you would say this is a dependent type, and this is a dependent type. My understanding of those, what the words are for there, that you would use them for, I'm more familiar with a dependent type theory in which you have these things, rather than them being specifically dependent types or not.
So when we talk about these things, are we going to say, oh, these are dependent types?
I think so.
Okay.
But that's more of a, I don't know how colloquial that is.
All right.
It ends up being a thing you say, certainly.
So we do something involving dependent types. It's going to involve these things, and we're going to see it all come together in the next slide.
Yeah, well, in a slide or two.
Or two.
It's-
Or three.
How are we going on time?
Usually we do an hour and a half.
Am I past that?
Yeah.
Oh, okay.
8:30 with 5 minutes.
Okay.
Much more comfortable. I mean, we're pretty flexible.
Well, okay, well, the slides will finish shortly, and then we'll be in the live coding section.
Okay. Yeah.
Okay.
We'll get to that.
Okay, a dependent pair is a pair in the way that we saw before, but this time the second entry, its type, can depend on the specific x that goes in the first entry, right? So I have this pair, and it's x times, but then like px of little x, right? So I'll skip through this a little bit, right? You have f in the, what you would call this the pi type. The same way that you think of pi as you write like for a big product, right? Big multiplication. Big product type, big logical and, you should think, right? Same thing with the sigma type, big sums, big sum type, big logical or, right? And that roughly models our notion of existence, right? There exists X such that P of X, right? And these are the notations for them in the formal literature. Not that I expect you'll be using them much, because I don't either. But that's if you ever see pi type, sigma type, that's what that means, right? A pi type is a for all kind of function, or the fact that the function exists and can run means that you have a for all statement. And the existence of a pair, a dependent pair, means that you have one member of the type family, which is true, at least. Okay, and here is a little table I've put together of all the different things you might see in logic or in mathematics versus their sort of type theory version. Top and bottom, sometimes you see this as like a fancy 1 or a fancy 0. Logical conjunction is your product type. Logical disjunction is your sum type. For all is your pi type. For existence, or there exists such that as your sigma type. Implication, just function types. Negation is a type alias, basically, just for P goes to empty. And then you can also make a product type out of implications to make a bidirectional implication if you want. Okay. Yep, that's the last one. We are now on to live coding. Did I put that over
You
there?
said Martin Love at the top.
Yes. Okay. Well, there
With
is
an umlaut.
yes. Well, actually, strictly speaking, I believe there's one thing that is missing here in order to make a full Martin Love type theory, and we're going to get to that very shortly. But, huh? Yeah, this is Beamer. Okay. Okay, this is not mirroring my screen, so I have to like look around very awkwardly. I should probably change the. Can I change the? This is not bright enough. Okay.
Thank you.
Here is the Haskell code I showed you earlier, and I just wanted to demonstrate no red lines. This is actually like valid code, which is like weird, right? It's like that. Like this is a proof. It's valid code. Also valid code in Rust. Those are yellow lines. I don't know if you can see very well. It's like I don't like your names for things. They should be capitalized in my preferenced way. But also valid code, right? Despite being theorems, right? You know, people talk about proofs as functions or functions as proofs. There you go. You can just write it in Rust, as long as it's not a dependent statement. Okay. Here.
Oh Lord.
Okay, you can ignore this. This is why I also have set up 0, which we're not going to look inside unless we really need to. But yeah, well, so Agda is another such a language that does things in Unicode, same thing as Lean. So we have our. Is this a size that everyone can see? Everyone's okay? Yeah. How about people at the back? Okay. Okay. So this is a funny plus sign with a dot on top, and we're using it to be our sum type. It is constructed in about the way that you expect, as you saw earlier. We have our true type. It has one constructor. People always use star for this. I don't know why, but I'm going to stick to that tradition. No constructor for empty type, as you saw. A bunch of
It's like kind star or something.
Huh?
Isn't it because it's like kind star or something?
I have no clue. Okay. So something about Agda. Who here has done a lot of Lean? Wow, that's actually relatively few, all things considered.
Part of this was to learn Lean too.
Yeah.
Actually, starting with this, it's very close to Lean too.
Okay. So
There was the differences too, but a lot of it.
yeah. So there's a bunch of like elimination rules stuff that you can do by default, just by like essentially by cases, in the same way that we showed in Haskell or in Rust. That is a little bit weirder when your thing has no cases. So we have the false elimination rule, which just says like I can make it's the trivial function from earlier. Like you give me something that proves false, I'll prove anything you want, right? And this in particular, sorry, I should say, that is a dependent elimination rules, right? So it doesn't assume that A is a particular type. A could be a type family, right? Okay. All right, we're going to start doing some exercises, and you're going to do them with me. So the way that Agda works, as I mentioned earlier, is not based on tactics, it's based on whole programming, right? So we have this function, and its function body is a question mark. And what I'm going to do, Control C, Control L, and you'll see, oh, what the hell? Oh, right, I have it open in Z. That's not what I'm supposed to do. I need to open this in VS Code instead.
HOL or HOLE? HOLE.
The question mark is a whole.
Got it.
Technically, it's higher logic.
Yeah.
Also, it's a hole in the type theory sense. So, technically, both things.
Well, have you ever done like an underscore line or underline in like Rust or Haskell because you weren't sure what to do there yet? Yeah, that's a hole too. And then you can actually like try to build it, and it will tell you like, here's the type of that hole. But an interesting thing about this is that because we are trying to do proofs here, we often don't care what goes in the hole, just that there is something that can go in the hole, right? So suddenly those holes become a lot more valuable because the particulars of what goes in them doesn't actually matter. If you can put something there and the type checker agrees with it, you're good. Okay. Oh, then this needs to be.
The operator, just so we can speak aloud.
Yeah.
Line 18, that operator.
The what now?
Underscore something underscore.
Where?
Line 18.
Underscore
Line-
plus dot underscore.
Ah, yes. So the way that Agda works is you can define things by infix, literally just like by putting underscores in them. Underscores in a like variable name when defined. Well, I shouldn't say variable. That's syntax for I turn these underscores into places an argument could go, and you can get really crazy with that. I will show you in a
I was
moment.
including the name you've chosen for that plus symbol with the slightly taller hat.
Well,
It has a dot
I
on top.
I didn't come up
It's
with.
a dot. It's
Yeah.
Okay.
I didn't come up with that myself.
That's fine. I just literally that explains it now.
A
Plus
lot,
the dot on
yeah. Well, so a lot of the way that I learned this is I watched half of the lectures and did half of the exercises for the 2022 Homotopy Type Theory Summer School, and a good half of these exercises are straight plagiarized from them. So I hope they are as educational for you as they were for me. Can I set themes? Go with something light. Okay. Okay. I should not be on that one. I should be on this one. No, that one. Okay.
Switch to a different program, but I don't know what it is.
This is I think this is like the open source version of VS Code. It's just like the Microsoft stripped out, which I didn't exactly do on purpose either. I just said Arch, Pacman install code, and this is what it gave me. So whatever. But okay, so if I do Control C, Control L, what is it doing? That's weird.
Question, I guess, is a powerful operator.
That's not supposed to happen. Now, can I get my which terminal has not that one? Restart this freaking language server. Ah, right, the language server isn't running. That'll do it. What?
What are you trying to do?
Get the type for the whole.
Yeah, the hole is supposed to do something. Hang on. I'm beginning to wonder if I have two language servers running and one of them's crashed.
You wouldn't be running with it. Pico.
That's not the worst idea, actually. Hang on.
Really the one that's actually says all done.
Ah, okay, here we go. There we go. That's something. What is it upset?
That's including in the extension.
Oh,
You may wanna
yeah,
restart
that's
VS Code.
pretty bad. Yeah. Okay, hang on. Oh.
You might want to kill Z too.
Yeah, not the worst idea.
In case it's trying to talk to your language server.
Well, so Zed doesn't actually have a language server for Agda, which is, huh? Oh, it's because I moved it. Well, hang on, but that's
It was late on time, so another option is to do a demo next time.
could do.
Yeah, I want to actually go through this.
Yeah.
I don't have the time.
Yeah.
Okay. Well, if people have to go, we can do this next time instead. Yeah.
Should we? Yeah. Should we?
Thank you.
Yeah. Let's all here
All right.
today.
I hope this was helpful. Sorry about the problems and sorry about running overtime. I can post these exercises on, huh? Oh, thank you. I can post these on the Discord if you like, if you want to get ahead of it. But I think it will be informative for some of these things to do them together, or I don't know, do them under any circumstances. We could do them like afterward. Yeah.
Are these slides posted on your website somewhere? Or?
No, I could put them somewhere if you want. But the stuff on my website is significantly more extensive about. It's all the same content, but elaborated a lot.
What is your website?
ClocksSugars.blog. So same as my Twitter handle. Clocks plural sugars, both plural. Yeah.
Join the Discord. There'll be a link in Discord.
Yeah, probably.
Also, I will. If you send them earlier, I can try to translate whatever makes sense to Lean, and we can.
Yeah.
During the Lean meetup, we can do them. Look at them in parallel and see what makes sense. Some of it would not.
Absolutely. Active contrast.
Yeah.
Yeah.
God, it's really a shame that this is
You
not.
said like, we'll put it in this column.
Well,
Is that correct?
yeah. Let's. Look, I know we all. Okay, we all programming language nerds. We need to withhold our excitement here because we got way too many languages basically.
Yeah.
So let's stick to the one that's in the title of the meetup.
Oh. Oh, that's now it's decided to do something.
And,
Oh,
it's okay to bring Agda to compare to Lean, but if we go all the ways to all the languages, it's not going to work.
So here you have
You probably need a theory to be able to compare this.
Yeah, well, yes, but it's also
What is a dot cabal?
Huh?
That's a
Go.
package manager. Yeah,
I
exactly.
really don't want to know.
Well, it's just cargo for Haskell. That's all.
Okay, yeah, but it compiles the
Do we have the camera still rolling?
Yeah, can we? Let's call it a day. Thank you,
Yeah,
speaker.
thank you.
Thank you.
Now we can go wild on the conversations about programming language.